So we want to start looking at linear combinations by exploring the relationship between a linear system, a vector equation, and a matrix equation. So I'm going to pick a linear system completely at random that we haven't even seen. I'm just going to write stuff down at random. I'm going to write x1 minus x2 is equal to 1, and 3x1 plus 2x2 is equal to 8. And then at this point, you're like, oh, are you going to use another system? I'm like, oh, no. This one is apparently my ride or die system. What we want to be able to do is take this linear system and write it as a vector equation. The vectors are going to be the coefficients of each of the variables. So my vector equation, if I look at this first part of it, this first column, just this part here, oops, sorry, just this part here, not big enough, just this part here. There we go. It's an x1 and a 3x1. So I'm going to think about, I'm not factoring out the x1, but I'm going to pretend that I'm factoring out the x1. I'm going to say in the vector equation, this will look like, sorry, in the vector equation, I think I just said a nonsense word. I'm going to write the x1, and I'm going to say multiply that by the vector 1, 3. So I took the x1 times 1, 3. And then to that, I'm going to add the x2 vector plus x2. That's just a scalar. And this vector will be negative 1, 2. And then to make a vector equation, this will equal the vector 1, 8. So that's the vector equation that goes along with, that's equivalent to the linear system. What we're saying is that what we're making here is a linear combination of the vector 1, 3 and the vector negative 1, 2. The left side of this equation is a linear combination of the vector 1, 3 and negative 1, 2. A linear combination is just vector multiplied by a scalar and then added together. So this left side of the equation is a linear combination of the vectors 1, 3 and negative 1, 2. And we write vectors as columns. So the left side of the equation is a linear combination of the vectors 1, 3 and negative 1, 2. And the equation is saying that this linear combination is equal to 1, 8. So the equation adds something to it, but it's a linear combination of vectors. So we can think of these two vectors as being a set of vectors, and this 1, 8 is a linear combination. We happen to know the solution to this system, which was x1 equals 2 and x2 equals 1. So 2 times 1, 3 plus 1 times negative 1, 2 will equal 1, 8, because we happen to know the solution. Because the linear system, the vector, and the vector equation both correspond to the same augmented matrix. So the augmented matrix is still by columns 1, 3, negative 1, 2, 1, 8. Oh, sorry. The question came up, what's the symbol between, this is supposed to be an and symbol. Mathematicians be lazy. So it's a combination of the vectors 1, 3 and negative 1, 2. So the linear system corresponds to this augmented matrix. This vector equation corresponds to the same augmented matrix. And we happen to know the reduced row echelon form here. We do row operations, and it was 1, 0, 0, 1, 2, 1, if I recall correctly. Yes, 2, 1. So what this means in terms of the vector equation, it means if I take 2 times 1, 3 plus 1 times negative 1, 2, I'll get 1, 8. So what that solution means is that if we take, oops, let me write the general solution over here. X1 equals 2 and X2 equals 1. So if I take 2 times 1, 3, if I take 2 times 1, 3, plus 1 times negative 1, 2, we get, let's see, add things up, 1, 8, just like we suspected. So that's all we're talking about when we talk about a linear combination. We're just adding up a bunch of multiples of vectors. Scrolling back up, we also want to be able to write the linear system as a matrix equation. So here's what the matrix equation is going to look like. I'm going to have a matrix of coefficients. The first column of the coefficient matrix will be 1, 3. The second column of the coefficient matrix will be negative 1, 2. This is getting multiplied by the vector x1, x2, and this will equal the vector 1, 8. In this case, we have a matrix. We've written the linear system as a matrix equation. So this has the form matrix A times a vector x is equal to another vector b. And it means the same thing as this vector equation. We are imagining the columns of the coefficient matrix as a set of vectors. The columns of the coefficient matrix form a set of vectors. The columns of the coefficient matrix form a set of vectors. Once we have a set of vectors, we can make linear combinations of those vectors. Any questions? We're going to have similar questions that we had with linear systems. How many ways can we write 1, 8 as a linear combination of the vectors 1, 3 and negative 1, 2? In this case, since there were no free variables, we can do this in exactly one way. Or even if we can write 1, 8 as a linear combination of those two vectors. Any questions? So that's what we're talking about with linear combinations. Let's take a look at so in problem 5 of the linear combinations notes, let's take a look at another example. So we have a set of vectors. These are my attempt at curly brackets. This is my attempt to write the word and. Oops. So in problem 5, we have a set of vectors and another vector b. So b is the vector, I'm just going to write it here. And I forgot what it was already. Negative 3, negative 2, 13. So b is the vector negative 3, negative 2, 13. S equals v1, v2, and v3. This is just a set of vectors. So when we're given, so we should also write down what v1, v, I should have just written them down here. So v1 is 1, negative 2, 3. v2 is the vector 2, 0, negative 5. and v3 is the vector 0, 4, negative 11. So we've got this set of vectors, and then a fourth vector, b. So the question that we might be looking at in this kind of setup, is the vector b a linear combination of the vectors v1, v2, and v3? So is b a linear combination of v1, v2, and v3? That's mostly what we do in this class, try to determine if one vector is a linear combination of another set of vectors. And then how many ways can we do that? And then can we simplify our set of vectors? So to determine it, we want to determine if b is a linear combination of the vectors v1, v2, and v3. So we want to determine if this, so another way to ask this is to say that is the vector equation x1 v1 plus x2 v2 plus x3 v3 equals b consistent? You can also write this as v1 times x1 plus v2 times x2 plus v3 times x3. I've always written my scalars in front of my vectors because my linear algebra professor wrote the scalars in front of the vectors. If you want to break that cycle, you can start writing the scalars afterwards. One thing that you may want to notice is that when I'm writing with like pens and pencils and such, when I write a vector, since I don't have a bold type on my pen, I just put a line over it. This is, I know in physics or in Calc 3, when you start studying vectors, you put little arrows. I don't have the energy to put arrows over all the vectors. I just draw a line over it. This is because mathematician, not physicist. And definitely not engineer. I don't have any kind of practical knowledge whatsoever. So another way to ask is b a linear combination of the vectors v1, v2, and v3 is to ask, is the vector equation x1 v1 plus x2 v2 plus x3 v3 equal b consistent? Another way to ask this question, to use a new term, is b in the span of the set of vectors v1, v2, v3. So another way to ask if this vector equation is consistent is to ask if b is in the span of that set of vectors. Any questions? It does look like average value, so we're just going to have to make sure that we're clear from context that we're not averaging, we're looking at vectors. So that's a new term, span of a set of vectors. The span of a set of vectors is a set of all linear combinations of those vectors. The span of a set of vectors is the set of all linear combinations of the vectors in the set. Talking about the set contains vectors. The span is all the linear combinations of those vectors. The notation we have for this, if you were wondering if there's notation for the span, it's like, oh yeah, this is a math class. Of course there's notation. So we could rewrite this question by saying, is B in the span of V1, V2, V3? And the question is this going to be the same process as in 1.1 when we were asked if the system is consistent or not? Absolutely. Like I said, the thing that we learned in 1.1 is the thing that we're going to be doing forever. It's the one thing that we do in this class. Because this vector equation corresponds to a linear system which corresponds to an augmented matrix. And so that's how we're going to get at what we want to find out. So we'll write down the augmented matrix. The first column is going to be 1, -2, 3. The second column will be 2, 0, -5. The third column will be 0, 4, -11. I'm going to make sure I note that this is an augmented matrix. And B is -3, -2, 13. Now that we've written down the augmented matrix of the vector equation, I want to know if it's consistent. So I'm going to have to enter this because I forgot to enter it in the beginning. So let's just enter this matrix. 1, 2, 0, -3, close brackets, open the next row, -2, 0, 4, -2, close the row, open the next row, 3, -5, -11, 13. Close the row, close the matrix, close the command, hit enter, and cross your fingers. It looks like we have a consistent system with many solutions. So if I get down to the reduced row echelon form, so the reduced row echelon form is going to be 1, 0, 0, 0, 1, 0, -2, 1, 0, and then 1, -2, 0. So that's the reduced row echelon form of the augmented matrix. And the augmented matrix does not have a pivot in the rightmost column. So the vector equation, the associated vector equation is consistent. So we say that B is a linear combination of the vectors v1, v2, and v3. We can say that B is in the span of v1, v2, and v3. Moreover, we can write B as a linear combination of the vectors v1, v2, and v3 in an infinite number of ways. What about this augmented matrix tells me that there's an infinite number of solutions to my vector equation? X3 is a free variable because it corresponds to a non-pivot column. X1 is a basic variable, X2 is a basic variable, X3 is a free variable. So here's X1, X2, X3, and our constants. X1 and X2 are basic, X3 is free. So that means there's an infinite number of solutions. Any questions? So the augmented matrix does not have a pivot in the rightmost column. Therefore, the vector equation is consistent. Therefore, B is a linear combination of the vectors v1, v2, and v3. Therefore, B is in the span of v1, v2, and v3. That's a lot. It's a lot of conclusions that we're saying that all mean the same thing. So what told us what was going on, what we observed, is that there is not a pivot in the rightmost column. Let's phrase it differently. Let's say the rightmost column of the augmented matrix is not a pivot column. Therefore, we can conclude the vector equation x1 v1 plus x2 v2 plus x3 v3 equals B is consistent. Notice it's the equation that I'm calling consistent. We can also conclude, this is equivalent to saying that B is a linear combination of the vectors v1, v2, and v3. Therefore, we're also concluding that B is a linear combination of the vectors v1, v2, and v3. Oops, got a little far with my arrows there. Since this equation is consistent, B is a linear combination of the vectors v1 and v2 and v3. We can say the same thing by saying that B is in the span of v1, v2, and v3. The way we speak this phrase is to say that B is in the span of v1, v2, and v3. This is tricky because we're also going to be using the word span as a verb, and we don't want to use it as a verb here. We could say B is in the span of the set S, v1, v2, and v3. We are concluding that B is in the span of that set of vectors. Any questions? All right. Mechanically, we're not doing anything new. Verbally, we got a lot of new terms that we need to put together and make sure that we say things correctly. Any questions? Comments? Snide remarks? One last thing that we want to point out is that notice that v3 is also a linear combination of the vectors v1 and v2. So note that v3, oops, let me reproduce this equation down here, or sorry, this matrix down here. So by columns, the reduced echelon form says 1, 0, 0, 0, 1, 0, negative 2, 1, 0, 1, negative 2, 0, because I have one more point to make. So this was x1, x2, and x3. So we have pivots in the first and second columns. The third column was not a pivot column. So there's another thing that we can notice about this set of vectors. This third column, if I just ignore what's going on with B over here, this third column is telling me that v3 is negative 2 times v1 plus 1 times v2. So this third column tells me that v3 is equal to negative 2 times v1 plus 1 times v2. That is, v3 is a linear combination of the vectors v1 and v2. v3 is a linear combination of v1 and v2. So in a sense, we don't really need v3, because if I need to build something that looks like v3, I can build it out of v1 and v2. So from this standpoint, we don't really need v3, because I can make v3 out of v1 and v2. What this means is that the set of vectors v1, v2, v3 is linearly dependent, because v3 is not really necessary. It's extra. We don't really need V3. This is not technically how we define linear independence. This is how we think about linear independence. Don't need V3. I can build it out of V1 and V2. Maybe there are some situations it'd be nice to have, but I don't really need it. It's like having a bard in your party. You don't really need the bard. It's nice to have sometimes, but I mean, they're the fifth member, and the first four can handle things just fine. You know what I mean? So we don't really need V3. So the set of vectors, V1, V2, and V3, is said to be linearly dependent. The set of vectors V1, V2, V3 is said to be linearly dependent because V3 doesn't really bring anything extra. No pivot there. V3 is a combination of V1 and V2. Don't really need it. If I take V3 out, notice that in the reducer echelon form, or those first two columns correspond to pivot columns. Though that the pivots indicate that we have something new, something important. So if I take V3 out, that's what's making this set linearly dependent. We can refine our set, and we could say the set V1, V2 is linearly independent. There are more rigorous definitions of independence, of linear independence, but this is how we want to think about linear independence. What vectors in this set do we really need? Because now, anything that I can write with the set V1, V2, V3, I can do that in an infinite number of ways. But if I take out the V3, every time I have a solution, I will have a unique solution. DVD bonus material, those are going to be referred to as coordinates. It's better if your address is always the same. You don't want 10 different ways to describe your address. You want one way to describe your address. Any questions? Comments? Snide remarks? Great, I'm going to stop the video here. And we'll talk about next steps.